Hello everybody, welcome back. In this tutorial, we're going to be covering quiz number 28, which focuses on strain energy. Now this personally is one of my favorite units because as you guys are going to see, strain energy, it's not a hard unit and basically it all comes down to one equation in which we just substitute values in. So this unit, very simple, very straightforward, but it's nice because, strain energy, it sounds really smart, but it's actually pretty easy for you guys. So that's good for me, that's good for you guys. It should be a win-win all around. So let's jump into the theory. So as I was saying for strain energy, it really comes down to one simple equation. Now for a linear elastic isotropic material, and I underlined that and made that nice and bold because again, this is for a linear elastic isotropic material, the strain energy density is given by the following equation. So if we look at this equation, it's 1/2 and then a bunch of sigmas and a bunch of epsilons and a bunch of gammas. Now, the 1/2, that comes from the fact that we have a linear material. So you notice up top, I say linear elastic isotropic material. Well, that 1/2 in that formula there, that's directly because this is a linear material. Now, again, this formula is for the strain energy density. So we're going to have to keep that in mind when we move forward. However, looking at this equation, we can see it's not too bad. It's basically just all the stress terms, sigma 1,1, sigma 2,2, sigma 3,3, etc., etc., as well as all of the strain terms, epsilon 1,1, epsilon 2,2, epsilon 3, etc., etc. Now, there's one thing about this formula that I'm going to have to point out because this will lead to a lot of mistakes. If we look at the normal terms, so 1,1, 2,2, 3,3, more specifically the strain terms, we have epsilon 1,1, epsilon 2,2, epsilon 3,3. However, when we look at the shear terms, so 1,2, 1,3, and 2,3, we don't have epsilon 1,2. We have gamma 1,2. So all of these shear terms here, instead of epsilon, we have gamma. Now keep in mind that gamma is simply 2 multiplied by epsilon. So therefore, if we're given something, say the strain tensor, we can easily find out what the gamma 1,2, gamma 1,3, gamma 2,3 is, not a problem. So if we look at this equation from a whole, it's not too bad at all. If I have both my strain tensor as well as my stress tensor, all I have to do is substitute values into the equation. I will have my strain energy density. Now, as I mentioned before, this is the strain energy density. So this will be what they're asking for 90% of the time. However, that extra 10% of the time, the instructor might ask for the total strain energy. And you're saying, wait, Clayton, total strain energy density, what's the difference? Well, think of density. It's actually exactly what we think it is. It's the density per cubic unit. So if we want to find the total strain energy, and again, I don't know the variable for this, so I just put TSE, all we need to do is integrate that strain energy density that we found above over the volume. And as you guys are going to see in question number 3, I'm going to show you guys exactly how to do this. It's not going to be too bad at all. Moving on to the next thing that we have to realize is the concept of strain energy components. So the strain energy density is actually comprised of 2 components, and those are the volumetric and the deviatoric strain energy densities. So when we go to these problems, most of the time you're going to be asked for the strain energy density, and then sometimes maybe they'll want the total strain energy. However, one other very common question, especially for you guys, since these exams are multiple choice and this makes for a great multiple choice question, it's going to ask for either the volumetric strain or the deviatoric strain or maybe both. Now this is nice because they follow a nice formula where the strain energy density U, it's equal to the sum of the volumetric strain energy as well as the deviatoric strain energy. So if we know those two, then we can actually find the strain energy density quite simply. So the question becomes, all right, Clayton, how exactly do we find those two? Well, starting off with the volumetric strain energy density, it's simply equal to P squared divided by 2K. So if we look at this, you say P squared, well, I don't really know what that is, and K, well, I also don't know what that is, so what do? Well, the first thing that we realize is that K there, that's the bulk modulus, and that's a function of both the Poisson's ratio nu as well as the elastic modulus E. So what we can do is we can substitute that into the equation. So therefore, our volumetric strain, as we can see, is a function of the Young's modulus E. You guys have seen that countless times. You guys are experts. And the same with the Poisson's ratio nu. And then the only last thing that you guys may not know, of course, is that P squared. Well, P is the hydrostatic stress. You're saying, oh wait, Clayton, I remember that. That was nice and easy. It is, because all it is going to be the trace of our stress tensor divided by 3. And you guys, oh, hold on, Clayton, I don't trace, who cares about trace? Just tell me what the formula is. Well, it's sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3, all divided by 3. So all we're doing is taking the diagonal components of that stress tensor, adding them up, dividing by 3, and then you can substitute that P into the volumetric equation. You guys are good to go for the volumetric strain energy density. Nice and easy. What about the deviatoric strain energy density? As we see, the deviatoric strain energy density is simply the von Mises stress squared divided by 6 times G. Now, if we look at the top there, the von Mises stress, well, you guys know exactly how to calculate that. It may not be the easiest thing to calculate, but we have that nice formula. We can easily find that von Mises stress if we know our stress tensor. The bottom term there, though, that's 6G. Well, 6 is just 6, that's not a problem. But G, that might confuse a lot of students, but G is actually going to be that shear modulus. And again, just like the bulk modulus, it's a function of both the Poisson's ratio nu as well as the elastic modulus E, which again, you guys have seen countless times. You guys know exactly what to do. So as we can see, both the volumetric and the deviatoric strain energy simplify quite nicely. They're fairly easy to calculate. And what's great about it is if we know both of them, then we can actually calculate that strain energy density no problem at all. So as we're going to see, we're going to go through the examples in the quiz here. Questions 1 and 2 will talk about this volumetric and deviatoric strain energy, while question 3 will talk about the total strain energy, while 4 is just kind of an ugly looking question that deals with strain energy in general. So let's jump into the quiz. Alrighty guys, welcome to the quiz. As you guys have seen, the quiz itself, there are 4 questions, but it's basically 3 questions because questions 1 and 2, they're basically the same question. Now, as you guys will see, I'm going to solve questions 1 and 2 through the iPad here because these make for great multiple choice questions. And in my opinion, if it's a multiple choice question, you guys should be able to figure out how to do it by hand. Now, once we look at question 3 and question 4, they're very ugly questions. Question 3 is ugly because it deals with a beam, and question 4 is ugly because it's not an isotropic material, it is an orthotropic material. And since those both get quite messy, I'm going to actually solve those into Mathematica. Now, when it comes to those type of equations on your guys' exam, as you guys are going to see, it simplifies quite nicely all the time. So what I recommend for an exam type scenario for questions 3 and 4, just copy down what you know the answer is going to be so you'll have it for the exam. Deriving it in an exam would actually be a lot of work, so I don't think that you guys will be asked to derive anything like that on an exam. Hence, I'm doing it in Mathematica and not showing you guys how to do it by hand. If I felt like you guys need to do it by hand, don't worry guys, I got your back, I would do it by hand. Now, looking at question 1 and 2, this is something you guys should know how to do by hand, thus I am also doing it by hand. So if we look at questions 1 and 2, they're the same in that it says a linear elastic isotropic material is under the following state of stress. So if we look below, we have our state of stress, our stress tensor sigma, no problems there. It says if G, E, and V are the shear modulus, Young's modulus, and Poisson's ratio respectively, determine. And it wants 2 things, those being one from question 1 and the other one from question 2. So question number 1 says, what is the volumetric strain energy per unit volume? And question number 2 is, what is the deviatoric strain energy per unit volume? So if we look at this, we have our stress tensor. All we need to do is figure out the values we need for each one of the equations and simply solve for it. So I'm going to come down here. I'm going to keep my stress tensor, as you guys can see, and I'm going to start with question number 1. If I just go to my pen there and don't be an idiot. And question 1 says, all right, here's our stress tensor, and we want the volumetric strain energy. So what I'm going to do is I'm going to write the formula for it. So strain energy is typically that uppercase U with the bar on top. But in this particular case, I want the volumetric. So I'm going to go U vol, and I'm going to write down the formula. So I remember that it was P squared all divided by 2 times the bulk modulus K. Now this is great, it doesn't look very complex, but again, if I look up at the question here, scroll up kind of slowly, it doesn't want anything in terms of K. It wants it in terms of G, E, as well as V. So there's nothing there that says it wants it in terms of K. So what I'm going to do is I'm going to have to rearrange this. But luckily for us, we know that K is a function of both the Young's modulus E as well as the Poisson's ratio nu. So what I can do is say, all right, well, this equation's not too bad. All I have to do is substitute what I know for K. So this is going to be equal to 3 multiplied by 1 minus 2 times nu. So that nu is the Poisson's ratio. All of this is going to be divided by 2 multiplied by the Young's modulus E, and then at the end we have our P squared. So now if we look at this, it looks much better. We don't know what nu is, or E, but it says that it wants the answer in terms of those two variables. So those two variables are not a problem. However, that P squared, well, it doesn't want the answer in terms of P, so we're going to have to figure out what P is. So if we come down here, we say, all right, well, we know that P is simply that hydrostatic stress. So P is equal to sigma 11 plus sigma 22 plus sigma 33 all divided by 3. So again, this right here, even though I wrote it out, this is actually called the trace of the the stress tensor. So I'm going to do is I'm going to switch my highlighter, and it's actually on dotted lines. I don't want that. So what the trace is, it's the sum of the diagonal components. So if I were to highlight these diagonal components here, this is what I'm taking the sum of. So very clearly, it's easy to see that sigma 11, sigma 22, and sigma 33 are all 0. So what we have for P is equal to 0 divided by 3. Well, of course, we know that this is just going to be 0. Now I'm going to switch colors because obviously we're taking this P value and we're substituting it up into the equation above. Well, we can see that if P is equal to 0, then our volumetric strain energy density in this case is going to be equal to 0. So I'm just going to scroll down a little bit. And I'm going to say, all right, for question 1, we know that U bar volumetric, so the volumetric strain energy density in this case is actually going to be equal to 0. And the reason why, well, we found that P was equal to 0, and that makes sense. This is based upon the volumetric stress. If we look up at our stress tensor right here, there is no volumetric stress because all of those diagonal components are 0. Now we're going to go down here and we're going to say, all right, well, question number 2, a little bit different, but kind of the same. It wants the deviatoric strain energy. So what I'm going to do is I'm going to put U bar. I'm just going to put dev, DEV. I'm not going to put deviatoric. That's a little bit long for me to spell. Chances are I'll make a mistake and make a fool out of myself. And I'm trying really hard to stop doing that with you guys. I know I do it so often, but I'm really trying. All right, so the formula for this one, it's not too bad. We remember that it's sigma von Mises, so that von Mises stress, squared, all divided by 6 times G. Now, what's nice for us in this particular problem is we're allowed to have things in terms of G. So that G at the bottom, that's completely fine. The only thing that we don't know in this case is going to be that von Mises stress. So what I'm going to do is I'm going to come down here and say, all right, well, I know the formula for von Mises stress. It's not nice, but I can easily figure it out, or easily, not easily. You guys know what I'm saying. We can figure it out. We have the brain power to figure it out. So one thing that I'm going to do is I'm just going to come up here really quick and we're going to look at this stress tensor. Now, it's very easy to see that sigma 11, so all our diagonal ones, sigma 11 is equal to sigma 22, which is equal to sigma 33, and all those are equal to 0. We kind of talked about that in question number 1. Now, another thing, if I were to look at the shear stresses, and I'll switch to a different highlight color for this one, so that'd be the 0, and then the P right here. We can also say that, all right, well, sigma 12 is equal to sigma 13, which are all equal to 0 again. So again, more zeros. And so the only non-zero component we have in this case is sigma 23, which is equal to P. And the reason why I'm showing you guys this is because this will make our von Mises stress equation very, very nice. So what I'm going to do is I'm going to scroll back down even a little bit further in this case, and we're going to go through the von Mises stress equation. So we know that the first major component is going to be sigma 11 minus sigma 22. Well, both of those are 0, so at the top here, we're going to have 0. And of course, it's squared. You guys don't really need the squared because you guys know it's 0, not a problem. And we say, all right, well, we're going to add this to the second component, which is sigma 22 minus sigma 33. Well, both of those are 0, so of course, the second component is also going to be 0. Move on to the third component. Well, that's sigma 11 minus sigma 33. Oh, wait a second. That is also equal to 0. So then we say, all right, well, those are all the normal ones. Now let's talk about the shears. So we go plus 6, and then it's all of the shear stresses squared. So sigma 12, well, we said that that's actually equal to 0, so we have 0 squared. Sigma 13, oh, wait, we also said that that's equal to 0, so that's 0 squared. And then plus sigma 12. Now, we remember above here, And I'll scroll back up just to show you guys. We see that sigma 23 is not equal to 0. In this case, it's actually equal to P. So what we're going to do when we come down here for this, we know that we have P squared. So what I'm going to do is we know that all of these terms are all divided by 2. And then I'm just going to end my square root sign for that von Mises stress. So it's pretty easy to see because everything kind of cancels. But in the end, we have 6 divided by 2, which is 3. So what I'm going to do is I'm just going to do the root. So yeah, instead of 6 divided by 2, we already know that that's going to be 3. And this is multiplied by everything inside those brackets. Well, we know that that is simply just P squared. So we know that our von Mises stress now, and oh, perfect, is simply root 3 times P squared. All right, well, that's not bad at all because, again, all we're doing is substituting everything into the equation. So we know we're going to take this and we're going to substitute it into the equation here. So what we can do is we can say, all right, well, it's equal to the von Mises stress, which we know is root 3 times P all squared, or not all squared, I guess just squared. And this von Mises stress is actually squared. So we know that this is all divided by 6 times g. And we say, all right, well, the square is going to cancel with the square root. So we have 3 times p squared, all divided by 6 times g. And this can be simplified even further because we know that 3 divided by 6, of course, is 1/2. So we know that the deviatoric strain energy is actually equal to p squared, all divided by 2 times g. So what I'll do is I'll come down here just to kind of state it a bit more clear. The deviatoric strain energy in this case is equal to P squared, all divided by 2 times G, where the G is our shear modulus, and that's it. That's the question. We're good to go. So as you guys are going to see, questions 1 and 2 here, they make for such great midterm questions because they can easily be solved. Now, I took my sweet ass time with it, of course, but you guys know that you guys can solve this in a matter of seconds. So these are, again, the 2 easy questions. Now we're going to move on to the 2 hard questions into Mathematica. So I will see you guys in question number 3. Alrighty, guys, welcome to question number 3. Question number 3, it's a little bit silly because if you guys may remember from your guys' assignment, it's the same question. So hopefully if you guys are watching this, you guys haven't started your assignment yet, and you guys can use this question as a nice, easy guide on how to do the assignment. Now, question number 3 says, the total strain energy due to deformation in a fixed ends beam under the action of a distributed load is given by L to the power of 5, so that's the length, multiplied by Q squared, where Q is, of course, the distributed load, all divided by A times E times I, where E, of course, is the Young's modulus and I is the moment of inertia. Now, the whole question wants us to determine what that factor A is. So A is kind of a poor choice, in my opinion, because a lot of people look at this and say, oh, well, that's the area of the beam, right? Of course, it's the area. No, 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 no. A is actually just a simple number. As you guys are going to see, the number is going to be equal to 1,440, and that's for a fixed ends beam. So the goal of this question is trying to find out what A is, and again, as you guys will see, A is simply going to be a number. Now, this question will take a little bit of elbow grease because it's going to be one of those Mathematica type questions. So we're going to jump on over to Mathematica and show you guys how to do this question. Alrighty, so I just opened up Mathematica, and as you guys have seen, I haven't started anything yet. I want to make this as true as possible to when you guys first open up Mathematica. So we're going to go through this all together. So the question wants the total strain energy. And as we know, in order to get that total strain energy, we need to integrate the strain energy density. So the whole goal of this will be to determine what U is. Once we have U, well, then we can simply integrate it. Now, of course, we know that U is equal to 1/2 multiplied and then by all those terms. So we have S11, so sigma 11 times E11 plus S22 times E22, etc., etc., etc. So I'll just go dot, 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 dot. Now, what's nice for us in this particular case is we're dealing with an Euler-Bernoulli beam. Mr. St. Clayton, that sounds complicated. And yes, it sounds complicated, but it's actually nice and easy for us because the stress components S22, S13, S33, as well as S23, they're all going to be equal to 0. And because of that, we actually get that our strain energy density is equal to S11 times epsilon 11 plus sigma 12 times gamma 1, 2. So remember, for those shear components, we're always multiplying by gamma instead of epsilon. Now, it gets even better for an Euler-Bernoulli beam, because what you guys will see is that epsilon 1, 2, which is directly proportional to gamma 1, 2, it's also equal to 0. So if this term right here is also going to be equal to 0, then our strain energy density is simply going to be this formula right here. And as we can see, this is really nice because we only need to know two things. One is sigma 1, 1, and the other is epsilon 1, 1. And it's easily seen in Mathematica because they're blue right now, which means that they're undefined. So what I'm going to do is I'm going to just suppress this for the time being, because this is something that we're going to get to later. And we're going to talk about how exactly do we get S11 as well as epsilon 1, 1. Now, as you guys are going to see, the key to this is going to be the deflection function. If we have the deflection function, we can easily find both S11, sigma 11, and E11, which is epsilon 11. So how do we do that? Well, we solve the differential equation. What I'm going to do is I'm going to magically put the differential equation on the screen here, and we're going to say, all right, so if this is the differential equation we want to solve, of course, we're going to use the dsolve function. How do we do that? Well, what I do is I go sol, which is basically saying my solution to this differential equation is going to be equal to, and then we're going to use our dsolve function. So since it's a function, we're going to have those nice square brackets. And again, we're going to take in three inputs. So there's going to be one here, and then one here. So the first input that we're going to want to enter is, what is our differential equation? So as you guys know, I typically like to define the differential equation above. So what I'm going to do is say, all right, well, dE is equal to the Young's modulus times the moment of inertia. And again, I put EM and IG because simple E and simple I are already taken. So I just do this to make sure I have a nice undefined variable, multiplied by Y to the fourth derivative. So I'm going to go 1, 2, 3, 4. And of course, this is going to be a function of x1. Now, another thing I do is I move that q to the other side, so I can go minus q, and this will be my differential equation. Now, what's nice in here is once I define what my differential equation is, I know that when I'm doing the dsolve function, I'm going to say my differential equation, well, that's going to be equal to 0. So again, that's what I want to try and solve for. The second input I need to argument is, all right, what equation or what function are you trying to solve for? Well, of course, this is going to be y as a function of x1. That's what I'm interested in. That's what I want to obtain. And finally, the last parameter is, what is the variable? Well, we know that is simply going to be x1. So if I run this right now, as I can see, no problem at all. It gives me everything I need to know. The only problem is I have these coefficients. And this is, of course, due to the boundary conditions or lack of boundary conditions. As you guys know by now, you guys have heard it so many times, we need boundary conditions to solve this problem. Luckily for us, we are given that this is a fixed end beam, so that's no problem. We know that for a fixed end beam, both of the ends are fixed, therefore they're not going to experience any deflection. So I know that y at 0, of course, must be equal to 0. We also know that y at the other end, so the deflection at the other end of the beam, well, that's also equal to 0. So now we have two boundary conditions. But as we see below, we have 1, 2, 3, 4 coefficients, so I need two more. Another property about fixed ends beam, there's no rotation at the ends. Anytime something is fixed, there's no rotation. And we know that the rotation is simply the first derivative of the deflection function. So I know that y prime, which is the rotation, at both ends is equal to 0. So I can go y prime at 0. We know that's equal to 0. And we know y prime at, y prime at L, so at the other end, we also know that this is equal to 0 right now. So now that I have my four boundary conditions, and if I run this now, as I can see, I have my solution. Now it's good to go. Everything's looking pretty sexy. We can move on. I say, all right, well, instead of having y1 approaches the solution, I just wanted to find y as the solution. So I can go y is equal to y of x1 when, and then I can go solution 1. Now when I enter this, no problem at all. Instead of having y defined as something approaching something, I actually just have it defined as our function right here. So this, of course, is our new deflection function. We're good to go. So what I'm going to do is I'm going to suppress this. I'm going to suppress this. Actually, I'm going to keep it. And now I'm going to run it again. And I did this because this is one of the questions I get asked for a lot. Remember, I just ran this It worked perfectly fine. But now I run the same thing, but now I'm getting an error. Well, here's the problem. When we do deal with these differential equations, it's always best to clear them every time we run them, or else one of them is going to be solved. It's going to be a problem. For instance, if I already know what y is, and Mathematica runs this code again, well then this right here, this isn't logical anymore, because it already knows what y of 0 is. So therefore, this will just be equal to yes, because we already know y of 0 is equal to 0, instead of it not knowing what y is. So what I need to do here is I need to, alright, let's clear y, and for good measure, let's clear solution. So now when I run it, it always goes back to normal, no problems at all. So now we have our deflection function y. And what I'll do is I might as well just comment this code so you guys know exactly what I'm doing. So the first step, that deflection function y. Now, as we see when we get into our sigma 1,1 component as well as our epsilon 1,1 components, we're going to need more than just the deflection function. One of the things that we're going to need is the moment function. So what I'm going to do is I'm just going to comment moment function so you guys know exactly what I'm doing. And we know that we can calculate this moment function from the deflection function, where our moment is simply EI. So what I have is I have EM times IG. It's not big G, not Instagram. All right, EM times IG multiplied by the second derivative of our deflection function. So derivative, of course, is that capital D, and inside it takes two arguments. The first one is what function do you want to differentiate? Well, we know we want to differentiate our y function. The second one is going to be, all right, which variable are you differentiating with respect to? Well, we know we're differentiating with respect to x1. Now, here's the key. I don't want to differentiate that deflection function once. If I differentiate it once, we know that that is simply going to be the rotation function. I want the moment function. I need to differentiate twice. So in order to do that in Mathematica, what I can do is I can put that x1 in squirrely brackets right here, and after I put x1, I can go comma 2. So this means I'm differentiating with respect to x1 twice. So if I run this bad boy right here, as we can see, we get a nice moment function as follows. So that's good to go. Now I come down, and what I'm going to do is I say, all right, well, now I have all the keys I need to find my stress component sigma 1,1. So I'm going to go S11 is equal to, and as you guys can see from the nice equation on the screen, it's simply going to be equal to -1 times the moment function multiplied by x2, and x2 is just x2. Here's one of the problems a lot of students try and do. They think x2 must be equal to something, but it's not. It's simply just x2. It's a variable. And all of this, of course, is divided by the moment of inertia, which I have defined as ig. So what I'm going to do, I'm going to suppress my moment function so I don't see it, and I can run my sigma 1,1. So now I got a value for sigma 1,1, which is great because if I look at my strain energy density, it has sigma 1,1 as a term inside of it. I already know what sigma 1,1 is. I'm good to go. What about the other term? And actually, I'll start deleting some of these spaces so I can keep all the code onto one page so you guys aren't getting too confused. All right, so the next term I need, of course, is epsilon. Epsilon. Yeah, I don't know how to spell, guys. It's a fact at this point. So epsilon 1,1. So we know that we also need epsilon 1,1. Well, just like before, it's actually a very simple equation for Euler-Bernoulli beams, where it's equal to negative x2, and again, x2 is just x2, nothing we need to do, multiplied by the second derivative of the deflection function. So just like we did before in the moment equation, we know that the second derivative is going to be y with respect to x1, and we want to do this twice. So just like that, if I run that, I now have epsilon 1,1, which is great. Good to go. So now what I can do is I can unsuppress my strain energy density formula right here, because now if I look at it, both S11 as well as epsilon 1,1 are now defined, so there should be no problem. So this right here is the strain energy density. So I'm just going to put that in, and I'm going to run it. As we can see, we get a big, long, disgusting mess. Now I want to talk about this big, long, disgusting mess because this is what a lot of students got when they did their assignment. Because again, this question is a part of your assignment. And they say, Clayton, I throw this into E-class and it's not quite working for me. Well, that's correct, because what we just solved for is the strain energy density right here. The question doesn't want the strain energy density though. It wants the total strain energy. So again, when we're trying to find that total strain energy, it's very simple if we have the strain energy density, but it's not equal to the strain energy density. If we look at the equation on the screen, we can see that we can find that total strain energy by simply integrating our strain energy density. So what I'm going to do is I'm going to suppress that. I'm going to come down, and our last section will be the total strain energy, which will be kind of the last part to this question. And we know that the total strain energy, which is what I just define as simply TSE, is the integral of that strain energy density. So what I'm going to do is I'm going to use the integrate command in Mathematica. It's a nice way to do integration. And all I'm going to do is I'm going to input two things. So there's going to be one column here. And the first one is, what is the function you want to integrate? Well, we know that is going to be our strain energy density U. So I simply put U here, looking pretty good. And then the second one is going to be, all right, well, what variable and what bounds do you want to differentiate with respect to? Well, we know we're integrating over the volume. So actually we're integrating 3 times, but let's focus on one of the integrals. Let's focus on the integral in the x1 direction. So I'm saying, all right, well, my first integral is going to be with respect to x1. So this runs along the length of the beam. So this goes from 0 to L. So what I do is I say, all right, I want to integrate with respect to x1. I want to start at 0, and I want to go all the way to L. So this will be my first squiggle bracket. Now, if I want to differentiate more than once, that's no problem in Mathematica. All I have to do is add another comma, add another set of squiggle brackets, and define what my next integral limit is. Well, I say, all right, well, I already integrated over the length of the beam. How about over the height of the beam? So the height of the beam is defined as the x2 direction, and I know that since my centroid goes through the, my x1 axis goes through the centroid of the beam, I know that I'm integrating from negative h over 2 all the way to h over 2. So now I've integrated both along the length of the beam as well as along the height of the beam. So now we have a double integral. But keep in mind, we actually want a triple integral. So we also need to integrate over the in-plane depth of the beam. So the the width of the beam into the page. So we know, of course, this is going to be the x3 direction. We know we're also integrating from 0, and we're going to the width of the beam, which is simply going to be b. So now when I have all this in here, I can run it, and I get this equation right here. Now, here's the second most thing I got asked about in the assignment. They say, Clayton, I entered this into E-class, and I'm still getting an error. Like, what's going on? I even remembered to integrate. I did everything you said. And if you guys have this answer right now, you guys are absolutely correct. Here's the problem that you guys have right now, is it wanted things in terms of L, which we have L right here, we're good to go. It wanted things in terms of Q. Oh, we got Q, so Q is good to go. It wanted things in terms of the Young's modulus E. Oh, we have that, we're good to go. And finally, the moment of inertia I, which we see here. Oh, we have I. So those are the 4 things it wants the equation in terms of. It does not say to have it in terms of B or H. So this is a problem right here. We need to get rid of this B as well as this H. Now, if you guys remember the moment of inertia formula, I is equal to base. Oh wait, I got a base right here, times height cubed. Oh wait, I got a height cubed here, and then divided by 12. So what I can do is I can rearrange that formula to say, all right, well, we know that B is equal to 12 times the moment of inertia, all divided by H to the exponent 3. So now if I define what B is equal to, when Mathematica outputs this answer, it'll substitute this in for B and do all the simplification. So all I did was define what the moment of inertia is equal to in terms of B rather than IG. Now if I run this bad boy, I get this final answer. And it's in everything in terms of what we wanted in the question. We have L to the power 5, Q squared, EM, and IG. And as we can see, that coefficient that we were asked to solve for, the missing coefficient, if you will, we now see that it's equal to 1,440. And that's exactly what you guys will have for your guys' answer at the end of your assignment for the fixed ends beam. The simply supported beam, it'll be the exact same formula. The only difference, of course, this coefficient will change. That should be the only difference. So that's it for this question, question number 3, guys. I hope the Mathematica tutorial kind of helped you guys. I'll scroll up a little bit to show you guys the code. I know a lot of you guys just copy the code, let's be honest with you guys. But that's okay. That's what I'm here for. If it makes your guys' life easier, I'm all for it. All right, guys. Thank you for listening to question number 3. Let's move on to question number 4. Alrighty guys, we're on question number 4, the last question of this little quiz. And as you guys will see, it's not too bad of a question. There's one major trick that'll throw off a lot of students, but once you guys get that trick, you guys are good to go. So question 4 says the strains in a linear elastic orthotropic material are given by the following strain tensor. So as we can see, we have a nice 3x3 strain tensor, and as we know, we can do a lot with this strain tensor. Now, the key to this question, and as I kind of said, the key that's going to throw a lot of students off, this is going to be an orthotropic material. We're so used to dealing with isotropic materials that once we get a material that's orthotropic, it kind of throws us off a little bit. It says, the material axes of orthotropy are aligned with the orthonormal basis set used. This is great. It means that we don't have to do any sort of change of basis. And it says the material constants are, and it gives us E11, E22, and E33. They're all non-zero values. And it gives us Poisson's ratio nu12, nu13, and nu23. But as we'll see, they're all equal to 0. And this is going to make our lives a lot easier when dealing with the elasticity tensor. And then finally, it gives us the 3 shear moduli, G12, G13, and G23. And luckily for us too, they're all equal to the same value of 35 MPa. Now, with this information, the question wants us to do 2 things. Part A, find the stress tensor, and part B, find the strain energy per unit volume. So that's the same as the strain energy density. As we're going to see, we have all the material or all the information we need to solve this question. Now, to make this a little bit easier, I'm going to go into Mathematica to solve this question because as you guys are going to see, orthotropic materials, they can get a little bit messy. And the reason why, well, the elasticity tensor. There's no way of simplifying that 6x6 elasticity tensor for an orthotropic material. So let's jump into MATLAB. MATLAB. I wish it was MATLAB. Let's jump into Mathematica and solve this question. Alrighty guys, so as you guys are going to see, the only thing I've done so far is define the parameters. I thought I wouldn't bore you or waste your guys' time with defining the parameters, so I already did that. I have E11 and E22 is equal to 100 MPa as given in the question. E33 is equal to 200 MPa as given in the question, as well as all the shear moduli being equal to 35. So instead of saying G12, G23, G13 all equal to 35, I just put G, and I'm just going to use G every time I see a shear moduli up here in my equations. Now, I also defined our strain tensor that we were given. So again, this strain tensor that I've already ran, this is something that we were given directly from the question. This just didn't appear out of nowhere. All right, so let's begin solving this question. I'm going to suppress this strain tensor because we're not going to really need to see it moving forward. Now, if we look at part A, the first thing that it wants us to do is find that stress tensor. As we know, it's very easily to convert from stresses to strains if we have our elasticity tensor. Now, the other thing we have to keep in mind is when we're using this elasticity tensor, we don't use strain tensors or stress tensors. We use strain and stress vectors. So what I'm going to do as my first step is I'm going to find my strain vector. And we can do this because we know all of the components of it from our strain tensor above. And I'm just going to run this really quick just to get rid of that output at the bottom there. It was kind of bothering me, probably bothered a little bit of you guys too. Let's see if I can make the code a little bit bigger for you guys. All right, so hopefully it's good to go now. Let's talk about our strain vector. So what I'm going to do is I'm going to find that as strain V. As you guys know, for strain tensors, I put strain T, and for strain vectors, I go strain V. Now I'm going to have the formula for the strain vector on the side here, and as we're going to see, all we're going to do is kind of pick little parts of our strain tensor and throw it into our strain vector. So the first thing that it wants in our strain vector, the first input, is epsilon 1, 1. So what I can do is I can go strain tensor, and we know that this is going to be component 1, 1. So I can go strain tensor 1, 1, good to go. We know that the second component in our strain vector is epsilon 2, 2. So we know that this is input strain tensor 2, 2, good to go. And similarly, the third one is going to be epsilon 3, 3, which I can go strain tensor 3, 3. So if I were to run this right here, as we can see, we took epsilon 1, 1 and made it into our first component down here. We took epsilon 2, which is the negative 0.2, made that our second component there. And then we took epsilon 3 over here and made it our third component in our vector. Now, we also have to consider the shear strain. So what I'm going to do is go comma, and we're going to start adding the shear strains. Now, if we look at the formula on the side here, as we can see, we have to multiply all of those shear strains by 2. It's more interested in gamma rather than epsilon. So what we're going to do is we're going to go 2 multiplied by epsilon 1, 2. So we know that epsilon 1, 2 from our strain tensor is simply going to be 1, 2. No problem at all. We can do the same thing. So again, when we're talking about shear strains, we have to go 2 multiplied by, and I'm going to go strain tensor. If I want epsilon 1, 3, well, it's just going to be 1, 3. Nice and easy. And I forgot to put tensor at the end there, so let's throw that in really quick. And then finally, we can have 2 times epsilon 2, 3. So nice and easy. I'll finish that there. And now when I run it, as we can see, we have a nice 6 column or 6 row vector. So the first 3 are epsilon 1, 1, epsilon 2, 2, epsilon 3, 3. And then finally, we have 2 times epsilon 1, 2, 2 times epsilon 1, 3, and then 2 times epsilon 2, 3. So now that we have our strain vector, we're good to go. We said the next thing that we need, of course, if we're converting from stresses to strains, is going to be our elasticity tensor. So this tensor is what we use to convert from stresses to strains. So what I'm going to do is I'm going to throw up this specific elasticity tensor on the screen. And as we can see, this is the tensor that we're going to use if we ever want to convert stresses to strains in an orthotropic material. So as we remember, isotropic material, we have a bunch of different tensors depending on our situations, whether it be plane stress, plane strain, something like that. If we see an orthotropic material, we always go back to this same elasticity tensor. Now, normally it's really hard to define, but as we can see, with all our Poisson's ratios being equal to 0, a lot of those columns actually cancel out 0. All right, so the first thing that we realize is it's 6 by 6. So what I'm going to need is to find 6 rows. So I got 1, 2, 3, 4, 5, 6. And what I should also do is separate each one of these by a column. So now I define the 6 rows. So now I got to go through and input each one of the rows. So if we look at the first column of the first row, we can see it's simply 1 divided by E11. All right, moving on to the second one, we see we have nu 21. Well, we know that all our nu's are equal to 0, so this is going to just be 0. And moving on, we see now that we have nu 31, which is also equal to 0, so this is going to be 0. And finally, the last are just 3 zeros at the end. Moving on to the second row, the first entry is nu 1, 2. Oh, well, hold on a second. That's also equal to 0. So that's not going to be a problem right here. The middle entry is 1 divided by E22. Well, that's actually defined. So 1 divided by E2. And then we say, all right, comma. And the next one, we have nu 2, 3. Oh, wait, that's 0. So 0. And then 3 more zeros. So as you guys can see, a lot of this is actually going to be equal to 0. Carrying on the same process, I have nu 1, 3 is equal to 0. I have nu 2, 3 is equal to 0, and then I have 1 divided by E3, 3. And finally, that's followed up by 3 zeros. That's kind of the first 3 rows, the most complicated rows. The next 3 are actually quite simple. So they all start with 3 zeros to start. And as we can see in that fourth row, it has 1 divided by G1, 2. Now we just have G because we already said, oh, well, if all the G's are the same, I might as well just define it as G. And then that's followed by 2 zeros. Moving on to the next one, I can see that there's 4 straight zeros, so 1, 2, 3, 4. And then I have a 1 divided by G, and then another 0. And then finally, I have 5 zeros in a row, and then that's followed by 1 divided by G. So what I'm going to do is I'm just going to go matrix form real quick, just to see what this looks like. And this is looking really good, because we know that all of these ones with the nu, they're all going to be 0. This is symmetric. We have 1 divided by E11, 1 divided by E22, 1 divided by E33, and then we have 1 divided by G for the remaining 3. So we know that our elasticity tensor is good to go, which is great for us because if we have both the strain vector as well as our elasticity tensor, we can solve for our stress vector. Now the stress vector, even though the question in the assignment asks for it, well, I guess it doesn't really ask for it, but it basically wants a tensor. Well, if we have all the components of the stress vector, then we know all the components of the stress tensor. So that's not going to be too bad. So going on to the next mistake is a lot of students will go, all right, well, this is easy. Our stress vector is going to be equal to our elasticity tensor multiplied by our strain vector. Nice and easy, right? Well, if I throw that in, I do get an answer, but as we can see, these are absolutely tiny. So there's a hint that we did something wrong. Now, I'm going to throw the equation for the elasticity, or sorry, I guess I never really got rid of it, but if we look at our equation for our elasticity tensor relationship, this is if we're trying to find the strains. Now, we know the strains. What we're trying to do is find the stresses. So what we actually have to do is inverse our elasticity tensor. All right, and that's because we're trying to find the stresses. In our original equation, as we can see there, that will solve for the strains. We already know the strains. We want the stresses. So now if I run it, we're good to go. So what we find, and we'll throw this bad boy into matrix form really quick so we can look at it nice and easy. We find that sigma 1, is 1 MPa, sigma 2 is negative 2 MPa, sigma 3 is 0.2 MPa, sigma 2 is 1.05 MPa, sigma 3 is 0.07 MPa, and sigma 3 is 0.14 MPa. So this would be the answer that we need for part B. And as we're going to see, most of the hard work has actually been defined for us once we get to that point. So that's how we do part B. Now we come down here and say, all right, well, next thing that we wanted is the strain energy density. Now, the key to the strain energy density in this case is that big long equation where we're taking sigma 1 times epsilon 1, and then we add that to sigma 2 times epsilon 2, and we go basically through the motions. Now, the key here is if we have those strain vectors, we can actually find this really easy in Mathematica. So what I'm going to do is I'm going to go U, which is that strain energy density. It's going to be equal to 1/2. So as you guys remember, the formula starts off with 1/2. Now, rather than writing the strain vector 1 multiplied by the stress vector 1 something like that, I'm going to use the sum function. So the sum function is going to be our savior here. And what we're going to see is it's going to take in 2 arguments. The first thing is, what are you always multiplying together? What are you trying to sum? Well, we always know that we're taking the first component of our stress vector, so I'm going to go stress vector of I, and we're multiplying that by the first component of our strain vector. So I'm going to go strain vector of I. So remember that we go sigma 1 times epsilon 1, then we go sigma 2 times epsilon 2, then sigma 3 times epsilon 3, etc., etc. And that's what I have here. I basically have sigma 1 times epsilon of 1, sigma 2 times epsilon of 2. The only thing that we have to do is define this I. So this is going to be in the second part here. And we're saying, all right, well, we're defining I, and we know that I starts at 1. And what we want to do is we want to go throughout the whole vector. So if we remember the vector, it actually has 6 components. So we start at 1 and we're going to end at 6. All right, so if I run this bad boy, I get that the strain energy density is equal to 0.0412, which is exactly what it is listed into the assignment. So it must mean it's correct. So if you guys are wondering how to do this question, this is exactly how you guys do this question. So that concludes this assignment, thankfully. It's a bit of a long one yet again. These assignments are always, these quizzes are always pretty long, but thankfully for you guys, it's done now. You guys are done. Quiz number 28. Only 3 more to go, guys. Can you believe it? We're almost done. So thank you guys so much for listening. I really appreciate it. I will see you guys in quiz number 29.